Hey everyone, Radzien here. In this video, we'll build a React app for tracking trading history on EVM chains. We'll use the Alchemy API to fetch transaction data and RadzionKit as a foundation to kickstart our TypeScript mono repo for this project. You can find the full source code and live demo in the description. We'll support the Ethereum and Polygon networks, defining them in a configuration file. Well, this setup could easily be extended to include a UI option for users to select their preferred networks. We'll keep the scope of this project small to avoid feature creep and maintain focus. We'll also define the specific trades we want to track. Given that the most common trades in pairs involve a stablecoin paired with ETH or robbed ETH, we'll designate ETH and VETH as our trade assets and USDC and USDT as our cash assets. A trade will be represented as an object with the following properties. It has an amount, an asset, which is the trade asset being exchanged, a cash asset, which is stablecoin USDC or USDT, a price, which is the price of the trade asset denominated in the cash asset, a type of either buy or sell, a timestamp for the time the trade occurred, and a hash, which is the transaction hash serving as a unique identifier for the trade. Our app will feature a single page where users can view their trading history and manage their wallet addresses. Since our app relies on an Alchemy API key to fetch transaction data, we'll ensure users set their API key if they haven't already. To handle this, we'll wrap the page content in the Alchemy API key guard component. This component checks whether the API key is set, and if not, prompts users to input it using the setAlchemyAPI key component. We'll store the API key in local storage so that users won't need to re-enter it the next time they visit the app. If you're curious about the implementation of use persistent state, check out the corresponding YouTube video in the description. In the setAlchemyAPI key component, we'll display our app's logo alongside an input field where users can enter their Alchemy API key. Instead of using a submit button, we'll validate the API key dynamically as the user types. To minimize unnecessary API calls, we incorporate an input debounce component to debounce input changes, ensuring the validation process triggers only when the user stops typing. To validate the API key, we'll make an arbitrary API call and assume the key is valid if no errors occurs. For handling and displaying the pending and error states, we'll use the match query component from RadzionKit. This component simplifies the rendering process by displaying different content based on the state of a mutation or query. Users can log out and clear the API key by clicking out the exit button, conveniently located in the top right corner of the page top bar. The content of our page is centered using a TLT that arranges elements side by side, trading history and address management. Since trading history requires at least one address to function, we wrap it with the address-only component. This component checks if the user has added any addresses and displays a message prompting them to add one if none are found. We store the addresses in local storage just like the Alchemy API key. This ensures that users won't need to re-enter their addresses each time they visit the app, making the experience seamless and user-friendly. The component for managing addresses is structured into three main sections. The first is header that includes the title and a visibility toggle. The second is the list displaying the current addresses. The third is an input for adding new addresses. To allow users to share their trading history while keeping their addresses private, we include a visibility toggle. The toggle status is stored in local storage, ensuring the user's preference is remembered across sessions. The Manage Address component displays an address along with an option to remove it. When the visibility toggle is off, the address is obscured with asterisk for privacy. The Add Address component enables users to input a new address. If the input is a valid address and isn't already in the list, it is added to the list, and the input field is cleared automatically. The component also respects the visibility toggle, obscuring the input field if addresses are set to be hidden. To display trades, we use the useTrades query hook to fetch the trade data. While the data is being fetched, a loading message is shown. If the query encounters errors, a warning block displays the error messages. The useTrades query hook returns an eager query object from RadzionKit, allowing us to display trades even if some queries fail or are still loading. This ensures a more resilient user experience by showing partial data when available instead of withholding all results. In the useTrades query hook, we iterate over the addresses and network specified in the configuration file. For each address and network pair, we create a query that retrieves trades using a getTrades utility function. This function utilizes the Alchemy client to fetch trades for a given address and return the data as an array of trade objects. Since the Alchemy client is used to fetch trades, we memorize its creation to prevent unnecessary client instances. By using a useQueries to eager query utility in the useTrades query hook, we aggregate the results of multiple queries into a single eager query object. This object provides a unifying source of data combining the loading states, errors, and results from all queries. This ensures a consistent and reliable data structure for the trades component, even when some queries are still loading or have failed. The Alchemy API provides options to fetch transfers either from or to an address, but it does not support retrieving both in a single request. As a result, we need to make two separate requests to gather all trades. To construct trades, we iterate over each transfer originating from the address. For each transfer, we first check whether the asset is a trade or cash asset. If it's neither, we skip the transfer. Next, we determine the trade type based on the asset's category. If the asset is a trade asset, the trade type is classified as a sell, otherwise it is a buy. Next, we look for a corresponding transfer that indicates the address received the opposite asset. If no such transfer exists, it means the asset was likely received from another source, so we skip the trade. Some swaps can be quite complex, so to simplify the process, we make a few assumptions. First, we assume that a swap won't take longer than 5 minutes. Second, we assume that during those 5 minutes, the user won't receive the asset they're trading to from another source. While it's possible to develop a more robust solution, we'll stick to this approach to keep the project simple for now. When searching for the corresponding received transfer, we first check the timestamp to ensure it falls within the 5-minute window. Then we verify the asset type. It should be a stable coin for a sell trade or a trade asset for a buy trade. With the from and to transfers identified, we construct the trade object. Most of the fields are set based on the trade type, leveraging a helper to handle conditional logic cleanly. With the trades prepared, we render them using a trade item component. This component displays the trade date, type, amount, asset, and rate. The trade type determines the color of the amount. Buys are displayed in a contrasting color, while sells use a primary color. We avoid using red and green to represent the trades, as a sell or buy doesn't inherently indicate a loss or profit. Above the list of trades, we display the current price and inform the user if it's a good time to make the opposite trade to the most recent one. To fetch the current price of the trade asset, we use the useAssetPrice query hook. We query the price of ETH, as both ETH and its roped versions on other chains should have a similar price. The getAssetPrices utility function retrieves the prices of multiple assets from the CoinGecko API. It takes an array of asset IDs and an option of fiat currency as inputs, then returns a record mapping each asset ID to its price in the specified fiat currency. By combining the Alchemy API for transaction data, CoinGecko for asset prices, and RadzionKit for utility functions, we built a streamlined app to track trading history on EVM chains. While this implementation makes simplifying assumptions, it provides a solid foundation for managing trades and exploring more advanced features in the future. That's all. If you liked the video, please like and subscribe.